the way I'm lecturing this is I'm just going to talk and sketch ideas down. And it's really to try and get this lecture's about doing good measurements and understanding what you're measuring, so that whenever you do anything else, like try and look at the kinetics or look at the impedance or do some spectroscopy at the same time, you know you have made good measurements. And electrochemistry is sold as a very easy technique, and to some extent it is an easy technique. Okay, it's very easy to get numbers out. The quality of those numbers is sometimes slightly open to question. So what we're trying to do is, especially for the new people, is ensure they're making good quality measurements so that everything else works. Okay. So what I'm going to do today is look at a simple reaction, what we actually are measuring when we do a measurement, how we can be accurate in that measurement, and then look at things like reference electrodes. So start off looking at simple cells and 2 electrode cells, and then go on and look at for what most of you will be the workhorse of your PhDs or postdocs, which is a potentiostat, and look at how a potentiostat actually works, and what it can do for us and what it can actually do against us and give us problems with. Okay, so that is the plan for the next hour and 10 minutes or so. That's roughly how long I'm going to speak, so we've got some time for questions at the end. Before I start off, just the other thing about this, it's a network. Okay, and that means you're all members of a network. You've all got equal rights. It's not just us lecturers who have got the rights to answer questions. You have got, if a question comes up in the chat and I haven't seen it, but you know the answer, yeah, you're a member of the network like everybody else. You type the answer you believe in. I might not know, electrochemistry is so broad, there's probably nobody who knows the answers to all the questions. But if you put a question up on this network, there's probably somebody, given there's 101 people who are all doing electrochemistry here, there's probably somebody who can answer that question. Okay, so don't be frightened. Don't just ask me. Ask the network. And if you put a question in the chat beyond this, it might not be might not be me answering it. It might be somebody else, and you feel that if you know the answer, just do answer it. Okay, and it may generate a discussion because somebody may disagree with your answer or may have a different interpretation, but let's use it as a proper network. Okay, so what I'm going to start off by concentrating on is what is a potential and what are we actually measuring when we just measure an electropotential. Why I said electrochemistry was popular at the beginning, there's only 2 measurements in electrochemistry, potential and current. Okay, potential tells us everything to do with the thermodynamics, and current tells us everything to do with the kinetics. Okay, so electrochemistry is simple. Potential, thermodynamics, current, kinetics. Okay, now there's lots of complications underpinning that, but that's all there is to electrochemistry, and they're the only 2 measurements I'm going to concentrate on today. But let's see what we mean by potential, and I'm going to start off. And I'm going to keep my life very easy and consider, I've been marking, so I've got the wrong color pen on. I don't want a red pen, I want a black one. Okay, so we're going to consider Fe3 plus an electron going to Fe2 plus. Okay. That is strictly real reaction I'm looking at is the ferricyanide one. So FeCN6 3 minus plus an electron going to FeCN6 4 minus. Okay, but just for shorthand, I'm going to write that as Fe3 plus an electron going to Fe2 plus. Now that is a totally reversible reaction. Okay, it is accepted in all textbooks. There are some papers out there that show it's not totally reversible, but it's accepted in all textbooks as being a reversible reaction. There aren't many totally reversible reactions. This one, ruthenium bipipi, are the 2 classic examples of reversible. And that's why whenever you go to any textbook, you find this reaction. Okay, and Reversible in electrochemistry, or reversible when we talk about electrochemistry, doesn't actually mean it goes backwards and forwards. It's not the chemical definition of reversible. When electrochemists use that term reversible to describe a reaction, they actually mean that it is thermodynamically reversible. And if you go back to your first year thermodynamics and you did a reversible change, then you had a, well, depends how they taught the thermodynamics, but classically you have a heat reservoir in the surroundings, and you keep the temperature of the surroundings or that reservoir always at the same temperature of the reaction. So you very, very slowly change the temperature of the reaction and at all the times you keep the surroundings at the same temperature by changing the temperature of the heat reservoir. Okay, and what that means is that temperature-wise, you're always in equilibrium. Okay, and that's what reversible means in this reaction. It means that it is always reversible. The Nernst equation always applies. Okay, you can never beat the Nernst equation. Okay, you can never change the system so quickly that the Nernst equation doesn't apply. So reversible in electrochemistry means the Nernst equation is always applicable. It doesn't mean it goes forward and backwards. Okay, so we're going to consider that reaction. Okay, and let's start off by just taking a beaker of electrolyte containing some Fe3 plus and some Fe2 plus and some nitrate ions to essentially say we haven't got any charge. And we need a source of electrons, okay? So let's make this a platinum electrode, okay? Electrochemistry, always expensive because they always use platinum, and they use platinum because it's an inert metal, okay? So you want it just to act, okay, there are examples when you're doing corrosion, you want an iron electrode because you want to study the electrode itself. But if the electrode is just there as a source of electrons, generally, we use platinum electrodes, okay? So when we have a platinum electrode, that is just a source of the electrons here. Now, as soon as I dip that platinum in there, I'm going to get some sort of equilibrium for this reaction. So if we add the Fe3 plus in excess, and some of the Fe3, then some of the electrons will go into the solution and react with the Fe3 plus, making Fe2 plus. So this has lost electrons, so normally it's now got a positive charge, and the solution has gained electrons, or it's lost Fe3 plus and got more Fe2 plus, still got more nitrate ions, so that will have a negative charge. Okay, and generally in thermodynamics, we look at the equilibrium of the reaction, do exactly the same here, but because this is now positive charge, becomes positively charged, that will be acting to stop the electrons. So we've got to take the electrostatics into account when we look at the reaction. So we're interested in looking at the thermodynamics of this reaction, okay? And what we're interested then in thermodynamics, normally we balance the chemical potentials. Now, because we've got different potentials or electrostatic potentials on the metal and in the solution, we've got to balance the electrochemical potentials. Now, electrochemical potentials, you write just as a chemical potential, so the electrochemical potential of species I, but you put a bar on the top. And all that bar says is, I'm looking after the electrostatics as well as the chemical potential. So it equals the chemical potential of species I plus the electrochemical, the electrostatic term. So the electrostatic term is just going to depend on the charge of the species times Faraday's constant. Okay, so typically in electrostatics you say it's the charge of the species, Q times the potential. But because this chemical potential is a molar quantity, we've got to make this molar. Okay, so the Faraday constant is just a charge on 1 mole of electrons. Okay, so that's just making everything molar. And then the potential of the phase we're interested in. Okay, and let's say phase alpha. Okay, the phase in which the species we're looking at is situated. Okay, now, what do I mean by potential? We have to be slightly careful here. So this is the Galvani potential. It is the potential of the electron, if we're doing in the metal, in here, in the metal. Okay? And it's not to be confused with the Volta potential. Okay? The Volta potential is actually the potential at the taking an electron from infinity. Okay, so you can look at these in two ways. We typically, when you talk about potentials, you take an electron from infinity, so a long, long way away. Okay, so at infinity to the phase. So here's our metal. Okay, and there's two potentials you could consider here. You could take it right up to the surface of the metal. Okay, and that, so the work done in doing that will depend on the charge on the electron and the the Volta potential, which is given the symbol psi, at the metal surface. Or you can take that electron from infinity into the metal. Okay, and that one is the Galvani potential. So the Volta potential is taking it to the surface. I might have just said that wrong. So the Volta potential, psi, is taking it to the surface, and the Galvani potential is taking it into the bulk of the material. Okay, and the difference between them is called the surface potential. So what I've got here is phi m equals psi m, the Galvani potential equals the Volta potential, plus the surface potential. Okay, that's the energy of taking the electron across that surface interface, which may have a dipole moment or something like that at it. Okay, I've pointed this out slightly because when you do the double layer, people just use the word potential, yeah, of the surface, and the double. When you do the double layer, you're actually, or when you do a Kelvin probe experiment, if anybody's done a Kelvin probe experiment, you're actually measuring the Volta potential. You're not measuring the Galvani potential. Okay? And some people at stages get muddled up between those two and try to go from one to the other. So just one warning, and a lot of this lecture is warnings about problems you get in electrochemistry. When people say potential, there are two, and we're considering, the local potentials. There are two values. There is the Galvani potential and the Volta potential, which are slightly different. Now, before anybody really panics if they're doing Kelvin probe experiments, okay, one of the things people assume in a Kelvin probe experiment is that as they change conditions, this is constant. So any change in the Volta potential equals a change in the Galvani potential because the surface potential remains unchanged. But that's an underpinning assumption that you should be aware of when you're doing your experiments. Okay, and lots of people talk about potential without going into that level of detail. Okay, so let's take this forward a little bit. Okay, and this potential here, our electrochemical potential of species I, we can the chemical potential, which we can write as the standard chemical potential, the chemical potential under standard conditions, plus a concentration term, how the chemical potential changes as I change species. And a concentration term in thermodynamics, just to be rigorous, should be an activity. Yeah, an activity is the thermodynamic concentration of species I. Okay. So we've got the thermodynamic concentration of species I plus the potential term. So when I my equilibrium across this interface, so across my interface of interest and my equilibrium, the sum of the chemical potentials of the reactants must equal the chemical potential of the products, or the sum of the chemical potential of the products. Okay, so for this very simple reaction we're considering here, we have the mu standard of Fe3 plus the concentration term RT log activity of Fe free plus the potential term. Well, the charge is now, the formal charge is now free F and phi, the galvanic potential of the solution. So the subscript S there is for the solution, plus the chemical potential, the electrochemical potential of the electron, which is just the chemical potential of the electron. We won't worry about concentrations of electrons, minus, because the charge on the electron is negative, minus F phi, and the electron is situated on the metal. So we're interested in the galvanic potential of the metal. And that must, so that's the sum of the electrochemical potentials of our reactants, and then the sum of the electrochemical potentials of our products. Well, in the product is only Fe2 plus, so it's the standard plus RT log activity of Fe2 plus 2F phi solution, because it's a 2 plus and it's in the solution. I see. So just collecting terms quickly here, I can write that the chemical potential of the metal minus the chemical, the galvanic potential of the metal minus the galvanic potential of the solution equals all those, collecting the standard terms, Fe2 plus, Fe3 plus, standard plus chemical potential of the electron minus chemical potential of the Fe2 plus, standard, over F minus RT over F, because log activity of Fe2 plus RT over F log activity of Fe3 plus. Okay. Now, if I define a standard condition, the standard condition is where the activities of Fe2 plus and Fe3 plus are 1. So those are both unity. So those go to 0. So under standard conditions, this term here equals phi m minus phi s under standard conditions. So I can write that, let's call that delta phi ms, standard. Okay, because that will go to 0, this will go to 0 under standard conditions. So this term will equal this term under standard conditions. Okay, so let me just rub that out. And so collecting all that together, I get that the potential difference across my interface equals the standard potential difference across that interface minus RT over F log activity of my products, the activity of Fe2 plus here, over activity of Fe3 plus. So I can measure the potential. So I can calculate, using simple thermodynamic theory, a potential difference across this interface up at the top here. Okay. So that's all thermodynamics done, except I can't actually measure that potential. To measure a potential, or what's sometimes called an electromotive force, I need to know, put a second interface in there and a voltmeter. So if I put a voltmeter here to measure the voltage, well, where do I put the other side of the voltmeter? I've got to put another interface in there. So whenever I'm doing a measurement of a potential, just potential, I actually have two interfaces. Okay? So I have a potential drop here and a potential drop here. Okay, and what I'm measuring is the energy required, the electromotive force, for moving an electron from here to here, or vice versa. Okay. So I'm always measuring, when I have a simple two-electrode electrochemical cell, to measure an electrode potential, I can't measure it. I've got to measure two of those. Okay, I've got to measure a potential or electromotive force, E, and that's going to be delta phi metal surface across interface 1, and by convention, interface 1 is on the right-hand side, minus delta phi ms of interface 2. So now, we can measure this potential, and it's related to two changes in galvanic potential across two interfaces in this case. Okay, so that's I can never separate these out. I'm always measuring two interfaces. So to make life easy for ourselves, what electrochemists have done is define the potential for one particular electrode as 0. Okay, the potential difference, this delta phi ms, equals 0, and then we measure everything else on the same scale. Okay, so we take the hydrogen electrode. So if I take a hydrogen electrode, so this has platinum black on the surface, which is just porous platinum, and we surround it. So let's put a jacket on there, in which we're going to bubble hydrogen. So we put hydrogen in there at one atmosphere pressure. And we have a second electrode, the electrode of interest. We have the redox couple of interest, so some Fe3 plus and some Fe2 plus. And we bubble hydrogen in and we measure a voltage. And we say that the potential across this interface is 0, because we have the standard hydrogen electrode. So we have H plus at an activity of 1. And then I can measure the potential then is the potential across the first interface, which I can write as the standard potential of Fe3 plus, Fe2 plus. And if they're under standard conditions, I can say that is the standard potential minus the potential across the second interface, which is 0, because by definition, and it's only by definition, when I have the standard hydrogen electrode, H plus H2, standard, then the delta phi ms2 equals 0. So I don't need to worry about, well, I can now work out a potential for a simple redox couple. Now, let's go back to old electrochemistry. Okay? So old electrochemists really trying to do very, very good work. Okay? And really trying to pin down a E0 value. And let's look how they did it. Okay? Not done often in textbooks these days. Okay? So let's look at somebody trying to do the standard potential for the silver chloride electrode. So they take the electrochemical cell, platinum, hydrogen, 1 atmosphere. And because you can share the electrolyte on this one, they just take HCl at some molarity, M, HECl, Ag. Okay, and we want to find this redox couple. This redox couple is under standard conditions. Standard conditions, unit activity. How do I make a solution of unit activity? Okay. It's not the same as the concentration. It's not 1 molar. I want to make a solution of unit activity. I can't really do that. So how do they do a really good measurement to get a really accurate to within 0.1 millivolt E0 value? So what they actually did was they looked at this equation and they wrote down the Nernst equation. So E of the cell equals E standard. Now, E standard right minus E standard left, but the E standard for the left-hand side is 0. So this is going to be just E standard for AgCl Cl minus RT over F log activity of products for the formal cell reaction minus activity of reactants for the formal cell reaction. So if I look at the formal cell reaction here, what it's going to be is AgCl plus H2 going to H plus Cl minus plus Ag. I've got that right. And is that balanced? No, I'm going to need two H pluses there besides that. Okay. Actually, let's do it with a half H2. It just makes my life easy. Half H2. That looks better because it balances the charge. Okay. So there we go. There's your balanced reaction. Okay, so that the activity of HgCl is 1, the activity of H2, because it's 1 atmosphere, is 1, the activity of silver is 1. So this is just going to be the activity of H plus times the activity of Cl minus. Okay, so the activity of H plus equals the molarity of the HCl times the activity coefficient of the positive ion, and the activity of Cl minus is going to be the molarity of HCl times the activity coefficient of the Cl minus ion. Okay, so if I substitute this into the equation above, I get that E cell equals E standard AgCl Cl minus, Ag, that should be. Horrible writing here, Ag. Minus RT over F log the molarity of the HCl solution, so molarity of HCl, strictly over N standard, 1, so that you're not taking log of something with units, okay, squared, minus RT over F log activity of plus times the activity of minus, or the activity plus, activity coefficient of plus times the, or activity plus minus squared. So they're being very good. They're looking, trying to look after, we're not just writing concentrations equal activities. We're doing the calculation properly. Now, for a one-to-one electrolyte, there's something called Debye-Huckel theory. And Debye-Huckel theory tells us that log to the base 10, so log of gamma plus minus, equals minus 0.509 times the molarity of the solution to the power a half. Okay, so if I substitute that into the Nernst equation we've got above, for trying to substitute for the gamma plus minus here, I get that the potential of the cell plus 2RT over F natural logarithm of the molarity of the solution, strictly over M naught, so it's dimensionless, okay, equals the standard potential I'm looking for, which is AgCl Ag, plus 2.34 RT over F times the molarity of the solution to the half. Okay, so using a Debye-Huckel correction. So the way old-fashioned electrochemists would do this reading, okay, is they would plot the right-hand side, left-hand side of that equation, E cell plus 2RT, the measured E cell, plus 2RT F log M, the concentration, and they'd vary the concentration of the molarity of the solution, and they plot that against molarity to the half. And they would have some points. Now, because the Debye-Huckel breaks down at high concentrations, it bends away from vertical, okay, from a straight line. But at low concentrations, so this is Debye-Huckel not working. But at low concentrations, they have straight line behavior, and they extrapolate that back to the axis to get the naught value. Okay. I wouldn't say anybody has done that experiment or been that rigorous for about 30 years. Okay. But rigorously, that is how you get E naught values. Okay? So, what do people really measure now these days when you see an E0 value in the literature. Because lots of people give E0 values in the literature. So what are they actually measuring? Okay, so when you see an E0 value in the literature, the E equals the E cell equals E standard cell, let's say, minus RT over F log, actual log, and they put concentrations in, okay, or they may put activities, okay, and the little trick you will see played sometimes, but not all the time, is that there is a dash there, okay, and that means they're measuring the formal cell potential, or the formal half cell potential. This is a formal cell potential because I'm doing it for a cell, not the standard reduction potential. Okay, so very few people these days measure standards. They typically measure the formal cell potential. Okay, and that formal cell potential, if you want to replicate their results or you want to report your results accurately, you should report, and you've just done a single measurement, you haven't done all this complicated stuff, you should report the concentration of reactants and products, and because it will affect the ionic strength of the solution, and the ionic strength of the solution affects the activities, the concentration of background electrolyte. Okay, and that cell potential that's reported by most people is actually only valid, and you should only be able to reproduce it if you're measuring at the same concentrations and the same background electrolyte concentration. Okay? And otherwise, you can get a different value. It's slightly different because it's, but okay, unless you've done the work of trying to, get unit activities or correct for the fact that, activities aren't constant, you don't get the same answer. Okay? So that's just a little bit. So going through this derivation of the classic Nernst equation, I think that everybody should have been familiar with the derivation of the classic Nernst equation, but the little bits extras are this idea of a formal cell potential, okay, which is strictly a, did I write it down? No, which is an E0 plus is the standard cell potential plus some RT log activity coefficient terms, okay, and also the other take-home message that I don't think everybody gets when they do electrochemistry from scratch is the difference between a Galvani potential and a Volta potential. So there are two things that are new. Okay, now, but modern electrochemistry began at a conference in Imperial in 1948, where people went from measuring potentials. Okay, so up until about 1948, and that's why there are these old methods, very accurate methods of measuring potentials. Modern electrochemistry began with measuring currents, and we'll look at that in a second. But the other thing I want to say here then, okay, is what we've measured here, because I set it up for the is the potential of the silver-silver chloride electrode. And of course, a silver-silver chloride electrode, once you've done the experiment accurately, is an alternate reference electrode. Okay, and reference electrodes are important. So in this experiment, you can measure, in the experiment I drew, you can measure the potential of a silver chloride electrode. So a more typical method of measuring a cell potential is to take a silver chloride electrode or a calomel electrode or something like that, so something like voltmeter, and then couple that to your working electrode. So there's your working electrode. This is your silver, this is a silver wire. This is a silver chloride on the surface. And here we have some potassium chloride solution. Now, different people use different reference electrodes. The classic ones are saturated potassium chloride solutions. And you know your solution is saturated because it's got some crystals of silver chloride, of potassium chloride in the bottom. Okay, this is your friend, okay, because it allows you to measure change or the standard potential or whatever potential you want across this interface, as long as this has its standard potential value. But how do you know it has its standard potential value? Okay. So the good electrochemist treats this with care. Okay. In some groups, okay, they're so careful with this, they have one standard reference, okay, because all your values you give as potentials now depend on this electrode. And if this electrode isn't working properly, all your potentials are wrong. So you really need to take care of this. Every evening or after every experiment, you take it out and you soak it in the correct electrolyte. So if it's a saturated one, you put it in a saturated solution of potassium chloride and you look after it. If you've got a 1 molar solution, some reference electrodes have 1 molar electrolytes, okay, in there. So in a 1 molar solution, you soak it in a 1 molar electrolyte. 3 molar potassium chloride, you put in a 3 molar electrolyte. And every so often, you check it. Okay, now what do you check it against? Well, one good idea for any electrochemistry lab is to have a standard reference electrode, okay, that everybody checks their reference electrode across. Perhaps keep it in the supervisor's office so it never goes missing. They always go missing. You end up buying hundreds of them. But anyway, or at least not hundreds, but tens. Okay? So that your students can check their reference electrode regularly against the agreed standard for the laboratory. Okay? Otherwise, the laboratory is actually reporting potentially rubbish because everybody's reference electrode is wrong. Okay? So there's one thing with, now that's a potassium chloride reference electrode. Now, what's here in the reference electrode is a glass frit. So that glass frit is going to let water through and it's going to let ions through. So the first thing to say is it's going to let water through. So I can't use this, or if you do see experiments done this way, reference electrode, potassium chloride, right? Take the potassium chloride, and I'm going to be doing, I don't know, an experiment in DMF. Okay, so you spent hours drying your DMF. Okay, and then you put a reference electrode in, and you take a calomel reference electrode. Okay, so now your DMF is wet. Okay, because the water is going to just leak through into your DMF. Because you can't, so yeah, so the other message with reference electrodes, choose the correct reference electrode for the experiment you're doing. Okay? If you're working at high pH, actually a silver chloride electrode doesn't work well at high pH. So if you're at pH 13, use a mercury oxide reference electrode. They're far more reliable at high pH. Okay? Clean your reference electrodes. Okay, the glass frit problem here, you often get salting in the glass frit. If a reference electrode is not working and all the wires look like they're connected, typically it's that you've actually got salting in the glass frit and you need to dissolve that salt out. So you take your reference electrode, put it in a solution of a water bath at about 90 degrees. That's normally enough to dissolve out the salts of crystallized in the frit there. If you're doing organic, you're using organic solutions, so DMF with a salt in there, 0.1 molar perchlorate, okay, then use a pseudo-reference. You often use a pseudo-reference electrode, a silver wire or a platinum wire, okay? And then at the end of the experiment, you add ferrocene and you see where the potential of ferrocene is and reference everything to that ferrocene. So what you do is you do cyclic voltammetry and have a cyclic voltammogram like that. And at the end of the experiment, you chuck some ferrocene in and run your cyclic voltammogram, and you'd have an extra peak in there because of the ferrocene. And the halfway potential of the ferrocene is very well known, so you do all your references versus that ferrocene. That's a good way of doing taking a reference. It may be okay if you're only looking at potential changes to use a pseudo reference. But if you're using a pseudo reference, be honest and quote it. With all reference electrodes, be very honest and exactly in your papers and publications say what your reference electrode is. Okay. And the other thing to say about the reference electrode is it's an extra interface in your system, particularly this one. Okay, so you've got a potential there, a delta phi across your metal solution interface there. You've got a delta phi there across your metal solution interface. But across here, you've also got a delta phi across your metal solution interface, across your glass frit, across the solution interface there. Okay? Because here, when I've got my glass frit, yeah, I've got solution here, K plus and Cl minus, and I've got a salt here, say I've got this is saturated, and I've got a 0.1 molar solution here of, say, sodium nitrate, you've decided is your. What's going to happen, okay, is of course the K plus and the Cl minus, you've got a concentration gradient, they're actually going to come out and the chloride ions will come out. Now, if I do that with sodium chloride, some people say, I've got no potassium chloride in my lab, I'm going to use sodium chloride. It's exactly the same, that the silver chloride, it's interested in the concentration of the chloride ion. It doesn't matter what the other ion is here, okay? So I take sodium chloride. What happens if I do sodium chloride here? Well, actually, there's a concentration gradient. This is saturated. So both will come out, okay? But the sodium will come out slower than the chloride ion, okay? So I'll get a lot more chloride ions coming out than sodium ions, okay? So what happens here is that I have a positive Galvani potential here, because I've got, and I have a negative Galvani potential here. So that's negative, that's positive, and I have a difference in Galvani potentials across that interface, across the frit. Okay? So I will measure that potential difference when I try and do my potential difference measurements. If I use potassium chloride, because their transport numbers are the same, or their mobilities of potassium and chloride are very, very similar, okay, they actually come out at roughly the same rate. So my potential difference across the glass frit now, or my possible difference in Galvani potential across the glass frit is 0, or close to 0. Okay? So that's what, so if anybody, you've all used potassium chloride, but the reason you use potassium chloride, which, old-fashioned electrochemists used to actually do these measurements, they're called transport number measurements, and they were classic lab experiments, is because so that you have or as close to 0 potential difference across that glass frit. So when I'm measuring the potential difference, let's go to a red, across this whole circuit here, this I don't need to worry about. And that's why I choose to use potassium chloride. Okay? So, or typically choose if I'm doing good measurements. Okay? So, now, there's another reason for not using a silver chloride or a calomel electrode, and that's if I'm doing corrosion measurements, a sniff of chloride will change corrosion of iron massively. So be aware that chloride is entering your system, okay, and it will actually change your corrosion measurements. Okay, so selecting the right reference electrode is important. In the Imperial College Library, there is a book, very old one, by Ives and Jantz, called Reference Electrodes. And if anybody's struggling with a reference electrode, it's worth a look. We did some very accurate with Mary Ryan, one of her postdocs. She was trying to do very, very accurate measurements where she wanted to vary the potential by about 1 millivolt, 2 millivolts. And she couldn't get them right, or the results didn't seem to match what was doing. And we had a long discussion on this, and it turned out that the reference electrode she wasn't waiting long enough for it to establish its potential. And the reference electrode, although it was I think it was probably a mercury oxide, because of the nature of the measurements, was taking about half a day to reach a stable potential. Okay, and then the experiment worked. But if you just took the reference electrode, because it was drifting through the experiment, the other part of the experiment didn't work. So your reference electrode is very, very important to get accurate measurements. Okay, so let's go on to the other part of getting good electrochemical measurements. Okay, well, there are other parts. Solution, make your solution properly. Okay, the quality of your electrolytes, so the quality of your water, you've got to get high quality, triple distilled water, reverse osmosis water. If you're using non-aqueous, then you have to get you've got to probably distill your solvents. Okay, you've got to polish your electrodes. Okay, one of the reasons mercury was used as an electrode in all the early electrochemical experiments wasn't that it was, a nice and liquid, although it's atomically smooth because it's a liquid, so that helps. But actually, it's because you could triple distill mercury. So old-fashioned electrochemists used to distill their mercury 3 times, okay, to get clean mercury so that their electrode was a good electrode and wasn't poison. All your background electrolytes. When I first started my PhD, I was using TBAP, tetrabutadiene perchlorate, and I had to recrystallize from alcohol 5 times, okay, to get good results. Degas, so remember to remove oxygen. Use argon or nitrogen to bubble through your system. I would argue, although you may need an argument with your supervisor, it's better to use argon than nitrogen, okay? The reason for that is that argon is heavier than air. So once you bubble argon through, it will sit above the top of the solution. Whereas because nitrogen's lighter than air, or slightly, okay, the nitrogen just goes away. Okay, so you get a jacket of argon above your solution, even once you stop bubbling. Now, your supervisor may argue argon is actually more expensive than nitrogen. They would be right, but actually the cost of the cylinders is so much higher than the cost of the gas that actually, there's not that much difference in price. Okay, so there are other things you must do to get good results. Okay, the other one is be able to use your potentiostat correctly. So we're now introducing current measurements, and the simplistic way to introduce current measurements would be, okay, there's my reference electrode. I'm going to measure a voltage, and I'm going to vary that voltage, and I'm just going to measure the current running through the circuit with my working electrode. Simple 2-electrode measurement, and I'm going to have an ammeter here, vary the voltage, measure the current. There is nothing wrong with that experiment, except for it's going to give you rubbish, okay? Because what's happening now is I'm passing a current through this interface, and I'm also passing a current through this interface. If I'm passing a current through this interface, I'm changing the concentration of, in this case, chloride ions, okay? But if this is a reference electrode, okay, the concentration of chloride ions, say I was doing a 1 molar reference, has to be 1 molar. The current's changing it. So this is no longer a reference point, okay? So when I change the voltage here, I change the voltage across this interface, and I change the voltage across this interface. And I don't know how that change in voltage is partitioned across those 2 interfaces. Okay? And because I don't know how it's partitioned across those 2 interfaces, okay, I'm just, essentially doing rubbish. Okay. So that doesn't work. Now, there are examples where 2-electrode measurements are done. Okay, so let's be honest. And where they are done, okay, is if I make this a microelectrode. Yeah. So if I'm doing SCCM, scanning electrochemical microscopy or something, where this is a microelectrode, Okay, now this current here is very small. Once this current is very small, I'm not really changing the concentration at this interface. The change in concentration at this interface is negligible. Okay, so some people, when they're using microelectrodes, will do two electrode measurements, and they are valid, but they're only valid because they're using very, very small electrodes and have very, very small currents. Okay, so in SECM measurements, you will get the nightmare with two electrode measurements that some people come across, and it's becoming more common, is that lots of people do electroplating, and they do electroplating in two electrode mode. So, you know, you have some metal that you want to plate onto, you have some big wire mesh here, and all you'll find in the literature is we dumped it in a bath of, you know, let's say we're plating copper, 0.1 molar copper, 2+ solution. We have a copper electrode, and we applied a voltage of 0.1 volts for 2 hours. Okay? It's impossible to, you know, okay, I'm going to do that experiment. That's what's reported in the literature, so I'm going to do that experiment. It's impossible to reproduce that experiment exactly. Okay? If you want to begin to reproduce that, you need the area of this electrode, the area of this electrode, okay? Because then we might know how, when I change the potential, it's partitioned across those. I also need to know the distance between the electrodes, because there'll be some IR drop there. Okay, so there's a resistance of solution. That resistance will depend on how far the electrodes are apart. So to accurately reproduce a two electrode mode electroplating, I need all the dimensions of the plating bath, dimensions of the electrodes, the distance the electrodes are apart, wherever both sides of the electrodes are exposed. Otherwise, and I can't exactly reproduce that experiment reported in the literature. Okay, it's very common now when people are electroplating just to say what voltage was applied. Okay, that's not telling you anything. Okay, and it's not useful. Okay, so let's just look at the time. Okay, so let's. So what we use when we're doing current measurements, so we want to vary the voltage and measure the current, is we use free electrode modes. So we have a working electrode, and that's the electrode we're interested in. We have a reference electrode, and we have a counter electrode. Counter electrode, secondary electrode, or control electrode. Okay? And essentially what we do in these experiments is we pass a current between there and there. So the current is passed between the working electrode and the counter electrode, and we measure the voltage, or we control the voltage, between here, the working electrode and the reference electrode. Okay? So current between the working and the counter, voltage between. Now, the impedance of the system is designed such that no current is now passed through the reference electrode, so that this is a true reference. There's no change in the concentrations at this interface. So we have a correctly working system. Okay. So let's have a look at how we do that in the electronics. Okay. So we have a control loop here. So we have a potential we want to apply. Call it a potential. Okay. And we feed that into a current, to an amplifier. Okay. Okay. So, and we ground one side of that, and that's the minus and the plus of the amplifier. And this comes out, and this goes, so here is our working system as our cell, and this is the reference electrode, and no current will be drawn up this arm. This is our counter electrode, and this is our working electrode. Okay, so this is a circuit that will allow current to flow between here, and set the potential between here and here. Now, if I gave set the potential between here and here to be the potential here, EI. If I gave this to an electronic engineer to look at, they would say the following, okay? The current through the cell is controlled by the amplifier. So that the ref electrode is minus EI, okay? So with respect to ground, Okay, so if that's true, if the reference electrode is minus EI with respect to ground, then our working electrode is at EI, okay? Or strictly at ground, okay? So the first thing to realize here is that actually you ground your working electrode. So in the default potentiostat, the working electrode is grounded. You can, in some, on most potentiostats these days, go into the software and choose to float your working electrode, which means actually they float that and they float that. Okay, but be aware your working electrode is grounded, typically. Okay, so if there is something wrong with your ground circuit in your lab, okay, that is going to affect your measurements. Okay, and the way to make something wrong with your ground circuit is actually, well, there's several ways to do it. Okay, if you're designing an electrochemical lab, so Antti Kusinak, I bet, has done this out at White City, you really want two main circuits. You want one that you plug your potentiostat in, and one that you plug particularly any vacuum pumps in. Vacuum pumps are horrible with your ground circuit. Okay, so if you have a vacuum pump on the same loop as your potentiostat, you'll find that you'll get leakage through to your ground circuit and things will not work nicely. Okay, the other ones are pulsed lasers. And pulsed lasers, when I was working at Bristol, where they do a lot of pulsed laser work, we had a horrible time with people with the pulsed lasers mucking up our measurements by mucking up the ground circuit there. Okay, so be aware of pulse laser of where you're grounding to. Okay? The other really interesting point about this sentence is how control works. Okay, most of us think when we're doing potentiostatic measurements, okay, that we're controlling the potential. Okay, and that's what we tell our software to do. Okay, we say in the software, if we're doing potentiostatic, I'm not going to do galvanostatic today. If we're doing potentiostatic, we tell our software to sweep the potential and measure the current in a cyclic voltammogram. Okay, but what your system is actually doing is it's controlling the current through the cell so that the potential is the one we tell it. Okay, so what actually happens in your electrochemical cell is actually we change the potential of the counter electrode so the current is such that the potential of this electrode versus this electrode is the value we told it to be. Okay, so what are the sort of implications of that for doing good measurement or using a potentiostat? Okay. So we talked about the reference electrode. That's good. Okay. The first implication here is that we're going to drive current. We're going to drive this counter electrode to have a certain current. And one of the rules of electrochemistry that is sort of written down but people don't understand is that the counter, as a rule, if you looked at it, everybody should say the counter electrode should be 10 times bigger in area than the working. So, you should use a platinum mesh because it's a high area electrode. Why is that? Okay. Well, the reason for that is that I'm going to have to pass current through this electrode. And this electrode I'm not interested in. So this, yeah, if I've got a positive current here, then I'm going to need a negative current here. I'm going to do a reduction at this electrode, and that reduction will just happen. Okay. But if I ask, if the current I want is, say, 2 microamps, okay, then this is going to have minus 2 microamps. What potential do I need to get 2 microamps through this electrode? Well, if it was a very, very small electrode, I might have to go to 5 volts to get that. Okay? And if I have to go to 5 volts, then I'm going to be breaking down my electrolyte and my solvent. Okay? At 5 volts, most solvents start breaking down. So if I'm using an organic solvent, I might be making some really nasty organic molecules there at my counter electrode. I've ignored them because we typically ignore what's going on at the counter electrode. Okay? If I make this electrode a lot bigger, yeah, I might only go to 0.1 volt here. Okay? To get the same current, because current just scales with the area of the electrode. Now, I might not be doing those horrible reactions that are breaking down my solvent. So that counter electrode, yeah, is 10 times bigger, so I don't need to apply a massive voltage to my count. So at least, you know, I might not know what reaction is going on there, or hopefully it's the opposite reaction of what's going on at my working electrode, okay? But at least it's not going to a high voltage where I have really no control, okay? Another thing we might want to do, because of that possibility that horrible reactions are going on at my counter electrode, is to put my counter electrode behind a frit, so that those products of that counter electrode reaction are not leaking into my system and interfering with it. Now, another thing that can happen at the counter electrode then is I drive it to, and this is something, you know, I have had students who have been, you know, when at ESAs or things, I say, oh, yeah, they'll say, oh, my system says voltage overload, but it's still working, so I just carry on. What does a voltage overload mean? Okay, and it's something lots of students get upset about with their potentiostat. You know, I said, yeah, you know, scan the potential between 0 volts and 0.1 volts. Okay? The manual says that I can go between 0 volts and 2 volts. Okay, now that's in the manual. You can scan between 0 volts and 2 volts. I've gone 0 volts to 0.1 volts. That's a lot less than the range, and it's saying voltage overload. That's not possible, so I'm just ignoring it. Okay, because I'm still seeing electroplating or something like that. So you'll still get plating, possibly, but it's gone voltage overload. What does voltage overload mean? Okay. Well, what a voltage overload actually means is that I've driven this potential of the counter electrode to the maximum possible, okay, and still the current isn't such that the potential between there and there is the set potential. Okay? So, what's the maximum possible voltage on this electrode? Okay, the maximum possible voltage on this electrode here is something called the compliance voltage of your potentiostat. Now, if you have a small potentiostat, that's typically 5 volts. Okay, so what it means if you've got a voltage overload is you've driven this potential to 5 volts, but still the current isn't such that you've got EI here. Okay? Now, so if you've got a compliance voltage problem, one thing to do is to take a bigger electrode, because I don't need to drive it to 5 volts to get enough current so that I get the correct potential now. An alternative is to take a bigger potentiostat. Okay, so a typical potentiostat these days, a particular big potentiostat, might go to 12 volts or 10 volts. An old EG&G potentiostat would go to 100 volts. Okay, a warning here. Okay, the rule is you always switch your potentiostat off before touching the electrodes. Okay, if you've got 5 volts compliance voltage, you're not really going to hurt yourself if you touch the system when it's live. Okay, at 12 volts, you're not going to hurt yourself. 100 volts, You will hurt yourself if you touch the system whilst it's live. Okay? So actually being aware what that compliance voltage is good for your safety. Okay? The rule is you always switch the system off before touching your electrodes. But, the safety aspect of that rule changes depending on what your compliance voltage is. Now, why might you want a high compliance voltage? Well, remember the current flowing in the voltage between your working electrode and your counter electrode, counter electrode and reference electrode. Okay, so I've got some current I'm trying to drive so that my voltage here is my set voltage. Okay, and the voltage I am applying here, because this one's earthed, will depend on how much voltage I drop through the solution, the IR. So if I've got really resistive solutions, I'm going to actually have to drive this to a higher compliance voltage. Okay, so if I've got organic solutions which are not very polar, so I can't get lots of electrolyte in there, so I can't get lots of background electrolyte in there, I might need to go to a higher compliance voltage. Okay, so you might need a bigger potentiostat to get your system to work. First thing to do is to change the area of your counter electrode, but if that isn't working, you need a bigger potentiostat. If you're ever purchasing a potentiostat, think about what experiments you're doing and what compliance voltage is required. And do a cost analysis, because actually the bigger the potentiostat, the more you're going to pay for it. Okay, so I think that is, well, okay, let's just, so VO load, there is always going to also be some IR drop here. Okay. Now, some people sometimes try and correct for that IR drop or reduce it. Okay, so there's different ways of, going back to our original drawings and trying to measure a potential. If I'm measuring a potential, it measures all potentials between the contact to the working electrode and the contact to the reference electrode, not just the potential across the two interfaces. So it measures that potential as well, the IR drop between the working and the reference. Yeah, that resistance between the working and reference is part of the potential. So when you apply a potential difference, it's not just the potential difference between the reference and the working, it's potential difference between the reference, the IR drop, and the working. So really you want to make this as small as possible. You want this to approach zero. Okay, so to get that to approach zero, you want the distance to be as small as possible. So some people work with get a glass blower to make a Lugin. Okay, so if you take a Lugin, you put your reference here. So there's your reference electrode, and then you have a very, very small glass capillary, okay, and you bring this glass capillary as close to the working electrode as possible. Okay, the potential here equals the potential here because there's no current flowing up this arm. Okay, so it doesn't matter that this can be a long glass capillary because there's no current flowing up this arm. It's only the current that's flowing past to go to my counter electrode that is important. Okay, the closer you get this, the lower your IR drop. There's other ways of dealing with IR drop, and I think you should be aware of how different systems deal with IR drop. Okay, some systems actually feed in an extra voltage into the system, so they plus a voltage for the IR drop. So you tell them what the resistance is, and then it adds an extra voltage to correct for that IR drop. Some systems do it in the software, and actually you get different results. So when you correct for IR drop, you should always say how you've corrected for it. Because those that do it in the software, okay, if I have a cyclic voltammogram that looks like that, and I'm correcting for IR drop, those that do it in the software only compress on this axis. Okay, so at this point, they've never actually applied the correct voltage. because if applied the voltage, it says plus minus the II drop. Okay, and then in correcting the cyclic voltammogram, they've changed the data on the x-axis to take into account the II drop, but they haven't changed the current. Whereas a true system, where you add extra voltage to the II drop, corrects on the y-axis, the x-axis, but also it's applied the actual voltage, so it's also corrected on the y-axis. Okay, so be aware how your system is correcting for II drop. And then the final thing is adding background electrolyte. Never forget to add background electrolyte to your experiment. And you do that for 4 reasons. Let's see if I can remember all 4. To reduce II drop. 2, to confine the region of drop in the volta potential, okay, so that the drop in the volta potential happens very close to the interface, okay? Otherwise, you have problems with different, okay? You haven't got well-defined points for where the electron transfer happens. Reduce II drop, confine. 3 will be to keep gammas constant. Okay. If you didn't have background electrolyte there, because you're changing the number of ions in your system, you're changing the ionic strength of your system, so you're changing the activity coefficients during an experiment. If I put a lot of salt in there, the ionic strength of the system effectively stays constant, because I'm only changing very, very slightly. So you actually have constant gammas in your system. Okay, so that's all I want to say about doing good measurements. You might have lots of questions about how you can improve measurements, but hopefully I've got you beginning to think about how to do measurements, and we can have about 5 minutes or so of questions, or we can go longer than that if we want, but let's see if anybody has any questions at this stage on what we've talked about. So if anybody wants to put their hand in the air or type questions in the chat, they are welcome to do so. Or they can put questions up later on. Okay, but you know, a day of good experimental design will save you lots and lots of time in the future and ensure that you get good, accurate results. Okay, so please spend time designing your experiments. Looks like people are too embarrassed to put questions in the chat or anything.
Jason, can I ask you something?
Yep.
So about the counter electrode, you said it should be ideally 10 times bigger. I mean, I guess you could get away with smaller if you know exactly what's going on in your system. But do you think it's always good to, for example, use a multimeter to measure the cell voltage whilst you are controlling the potential of one electrode, just to see?
I don't typically do that. Sometimes in the software you can do it anyway. I think possibly if you're having problems, it's probably a good idea. Mm-hmm. Yeah. But the first thing to do when you're having problems, just going back here, let's go back to this diagram here. The other thing, if you've got a voltage overload, and you know, the supervisors do this all the time. You know, students come to their door, knock on the door, and say, "I've got a voltage overload. I can't work out what's going on." They'll walk into the lab. Yeah, they'll walk into the lab, and what they'll do is they'll flick the reference electrode, okay, and then they'll walk back out, and the system will work, okay. And the first time you see this, what normally has happened is that in the bottom of the reference electrode, you've got a bubble, okay? Mm-hmm. And as soon as you've got a break in that circuit, you can't measure a voltage difference between there and there. So what happens when that happens is that it just drives your compliance up to 100 volts. It's got 100 volts, yeah, and it's got to 100 volts, and you're still measuring 0 volts actually between your counter and your reference, because you can't measure a voltage. You've got a break in the circuit, and your counter electrode is bubbling around along at 100 volts, and it's got voltage overload because actually there's no voltage because of that bubble. Your supervisor's walked in, flicked the reference electrode, the bubble's floated up, put the reference electrode back, and your system's now working because you've got a complete circuit. So the first thing to do whenever you see a voltage overload is flick the reference electrode or check your contacts. Okay, but if you're in a classic voltage system.
So we have a potentiostat which has a display right on it so that you can immediately see the potential of your electrode in whatever configuration as soon as you've done your connections. And when it starts to oscillate -2, +2, when it really is going all over the place, that's normally an indicator that you have a broken connection. Normally when you have a steady value that doesn't change too fast, that's normally an indication that, okay, your connection's okay, but your equilibration is taking a while. So then on potentiostats which don't have such a display, we always do an open circuit measurement at the start of every experiment, just to A, see that there's a connection, and B, to check that problem that you described before with the reference, with the equilibration taking a while.
Yeah, there's another time to do that, checking the circuit before you start, and that's if you spent 5 days making your working electrode, and you switch your potentiostat on and you have got a broken contact, it'll drive the voltage to somewhere that can destroy that 5 days work.
Oh yeah.
Yeah. So the more valuable your electrode and the more time you spent preparing it, the more it's worth checking all those things before you switch your potentiostat on.
Indeed. Ivan?
I think there's someone else who's got a question.
Yeah.
First.
Derek.
Oh, hi.
Hi.
I got a question regarding the proper grounded potentiostat. What can we see on the software on the monitor if the potentiostat is not properly grounded?
Okay, that's good. What I say in the monitor, if you actually look through the manual, somewhere in the software, typically, and it'll depend on how much you've paid for your potentiostat, you can actually choose to float the potentiostat. So certainly a Solartron 1286 you can float, and I think a EG&G you can float, but it depends on the software. Also, it's worth also remembering to ground your Faraday cage as well to your potentiostat, so that they're all at the same ground. Okay, so if you are using a Faraday cage, please ground it.
Okay, thank you.
Okay.
Thank you very much.
Ifan?
So